Hello and welcome again to Math County. So in the previous video, we started talking about the indeterminate forms and L'Hopital's rule, right? So we spoke about the indeterminate forms 0 over 0 and then infinity over infinity, right? So here we are going to talk about other variations of the indeterminate forms and see how best we can handle them. Great. So first, we are going to talk about the indeterminate difference. Okay, so what is the indeterminate difference all about? So if you have a function like this, where limit as x approaches a of f of x is equal to infinity, and another function limit as x approaches a of g of x is equal to infinity, and then we subtract these two functions as we take limit as x approaches what? A value a. If our indeterminate form is what? Infinity minus infinity. This is how we handle it. So we'll look at this example here where we have limit as x approaches 1 from the left of 1 over x minus 1 over x minus 1. So what do we do here? First, we set the limit point to see what is happening. So if we set the limit point, we have 1 over ln of 1 minus 1 over 1 minus 1. So clearly we can see that we have 1 over 0 minus 1 over 0. And this gives us infinity minus infinity, right? So what do we have to do? We can manipulate this function here so that at the end of the day, instead of having the indeterminate form infinity minus infinity, we end up with the indeterminate form 0 over 0 or infinity over infinity, right? So simply we are going to find the least, the common factor for these functions, and then say that ln x times x minus 1, right? And then we have x minus 1 minus ln x. Good. So we realize that if we insert 1 into this function, we end up with 1 minus 1 minus ln 1. And then we have ln 1 to bracket 1 minus 1. Now, if we watch closely, we will see that the numerator ends up with 0 because ln 1 is 0. So we get 0 over 0. And this is a very, it's an indeterminate form that we can all recognize. So clearly here, we can now comfortably use L'Hopital's rule to solve this problem. So what does L'Hopital say? L'Hopital says that if we have such an indeterminate form, what we have to do is to differentiate the numerator and then the denominator, and then test what happens at the limit point. So we can let f of x be equal to x minus 1 minus ln x. Then f prime of x will be equal to what? Will be equal to 1 minus 1 over x, right? Because this will be equal to 1, this is 0, and this is 1 over x. So we have g of x to also be equal to, our g of x is ln x times x minus 1. And if you apply the product rule here, we end up having g prime of x as x minus 1, 1 over x plus ln x. So if we insert this into the function, we are going to have limit as x approaches 1 from there, right? Of 1 minus 1 over x all over x minus 1, 1 over x plus ln x, right? If we simplify this function, we have limit as x approaches 1, x minus 1 all over x minus 1 plus x ln x. And again, when we insert 1 into this function, we are going to have 1 minus 1 all over 1 minus 1 plus 1 ln 1, right? Good. Now that we have this, the rule says that so far as we continue to have the indeterminate form 0 over 0, we can continue differentiating the numerator and then the denominator, right? So again, we are going to differentiate f of x, which is now x minus 1, and then g of x, which is now 2x minus, sorry, it's not 2x, which is now x minus 1 plus x ln x. So clearly, f prime of x will be equal to 1, while g prime of x will be equal to 1 plus x 1 over x plus ln x, right? So this cancels this, and then we have 2 plus ln x. So we can insert that into the function. And then we have limit as x approaches 1 of 1 over 2 plus ln x. And guess what? The answer is 1 over 2. Right? So you can see very well that Hopital's rule is quite efficient. So we will look at another example, and then we'll look at another variant of the indeterminate forms. So we have a question here that says that we should calculate the limit as x approaches infinity of e raised to the power x minus x. Right. Now this here is quite a simple one. What we can do is we can say that limit as x approaches infinity. What happens when we substitute e raised to the power x out of this function? If we bring e raised to the power x out, we are left with what? 1 minus x over what? E raised to the power x. Okay? So now, let's look at this. As x approaches infinity, right? If we consider this side, which is limit as x approaches infinity, here of x over e raised to the power x. Clearly, e raised to the power x approaches infinity exponentially fast, right? So what happens here is that as x approaches infinity, this approaches 0, right? So if this approaches 0, then limit as x approaches infinity of e raised to the power x times 1 is equal to what? Will approach infinity. Good. So Okay. We'll look at another type of indeterminate, another variant of indeterminate form. So now, if we have limits as x approaches a of f of x raised to the power g of x, then if we say that if limit as x approaches a of f of x is equal to 0, and limit as x approaches a of g of x is equal to 0, then we have the indeterminate form 0 raised to the power 0, right? 0 raised to the power 0. Good. Now, if we have limits as x approaches, sorry, this is f of a, or yes, this is f of a. As x approaches a, f of a equals infinity, and limit as x approaches a, g of a equals 0, then we have the indeterminate form infinity over 0, right? And then if we have limit as f of a approaches 1, and then limit as g of a approaches infinity, then we have the indeterminate form 1 raised to the power infinity, right? So usually what we do in this case is we use the natural logarithms to solve this problem. We will take a couple of examples and I'm sure it will be clear in a jiffy. So we have a question here which says that we should calculate limit as x approaches 0 of 1 plus sine 4x raised to the power cot x. So what happens when we put in cot x, right? So as x approaches 0 from the right, we have 1 plus sine 4x approaching 1, because we have sine 0 here, which is 0, so we are left with 1, right? What about cot x? And cot x will approach infinity. Therefore, we have the indeterminate form 1 raised to the power infinity, right? Good. So what can we do in this case? We have such a question. We can say, let y be equal to the function 1 plus sine 4x raised to the power cot x. And then we will take the natural logarithm of both sides. We can say that ln y is equal to ln 1 plus sine 4x. Sorry. One plus sine 4x raised to the power cot x, right? And we know that This is the same as saying len y is equal to cot x len 1 plus sine 4x, which is also the same as saying len 1 is equal to len natural log of 1 plus sine 4x all over what? Cot x, right? Good. So now, from here, we can insert our limit point to see what happens. Okay. Now, if we insert our limit point, what do we get? We still get our 0 over 0. So we can apply L'Hopital's rule here. Right? We can apply our L'Hopital's rule here. So we differentiate the numerator and then we differentiate the denominator. Now, if we differentiate the numerator from here, we can see that we will have 4 cos 4x all over 1 plus sine 4x all over, this is what? We differentiate cot x and we have sec squared x. This should be easy, right? So what do we do when we have to differentiate this function? We know that if we differentiate the entire function, we have 1 over 1 plus 4x. And then we differentiate what is inside the bracket, and then we have 4 cos 4x. Okay? Watch my videos on differentiation, and you will see how to work this out. All right. So now that we have this, right, we can now insert our limit points. So we have to find our limit as x approaches 0. And clearly, this gives us 1, because 0 is 1, sine 0 is 0. So we have 4 over 1 all over sec squared x. So sec squared 0 is 1. So we have our answer as 4. Good. So now that we have this, don't forget we have len y to be equal to what? 4. Hence y will be equal to e raised to the power 4. Good. Let's solve one more example and then we can end our discussion on indeterminate forms and L'Hopital's rule. So we are to find a limit as x approaches 0 of x raised to the power x. Okay, so clearly here, if we insert the limit point, which is 0, we have 0 raised to the power 0, right? Which is one of the indeterminate forms. So here also what we can do is, we can say that x raised to the power x is equal to e raised to the power len x raised to the power x, right? And then this is the same as saying e raised to the power x len x. Okay? So now, we have already discussed and we have already seen that the limit as x approaches 0 of x len x is equal to 0. Right? Now I employ you to try this out and then confirm that this is true. Right? But if you have forgotten, we can say that from here, ln x is this over 1 over x. Right? And this gives us what? Negative infinity over infinity, which suggested that we can apply L'Hopital's rule. So we differentiate the numerator and then the denominator, and then we have 1 over x over minus 1 over x squared, which is now 1 over x times minus 1 minus x squared. This cancels this, and then we have minus x. Therefore, we have the limit as x approaches 0 of x ln x to be equal to what? To be approaching 0. Right? Good. So, in that case, we have this function here, which is what? Limit as x approaches x, which is now equal to limit as x raised to the power x as x approaches 0 of e raised to the power x ln x is equal to e raised to the power 0, which is equal to 1. So this brings us to the end of our discussion on L'Hopital's rule and the indeterminate forms. I'll see you in the next video. Bye-bye.